In addition to the column length, one can also consider the gel column composition. So with SDS page here, we're dealing with the percent total acrylamide, the percent T of the gel column. And it's exactly as you would expect with SDS page. The lower percent T affects faster separation, so we move to larger molecular weight proteins in a shorter period of time. But if you want to do separation of lower molecular weight proteins, then you move to a higher percent T. What's shown in the image in B is that we can essentially change the curvature of these separations. So part A, we're looking at separation in time, and in B, we're plotting the fraction number. I'll mention here that the timing of the fraction collection intervals can vary, and you can customize it to whatever you want. But realizing that as larger proteins migrate from the gel, the larger the protein, they move slower. So in order to try to trap these proteins in single fractions, we collect them over longer periods of time. So our trapping intervals move from 1-minute fractions to up to 15 minutes per fraction. And what you end up getting is what looks like a linear separation, but realizing that this is on a log scale. But what you can also think about with that is that you can essentially provide the resolution where you want it the most. So if you're interested in collecting the large molecular weight protein, you would do so on a low percent T column. This is a 5% gel, and you can see that we easily collect and trap proteins exceeding 250 kilodaltons. But if you're only interested in the low molecular weight proteins, well, then you would use a high percent T column, and we see here that we can collect our fractions over the mass range of about a little less than 10 kilodaltons up to 50 kilodaltons. And by doing that, I think it's very realistic to see that the GELFrEE system can provide a much larger number of fractions, and I believe that 50 GELFrEE fractions is certainly a possible goal for us. We're always interested in protein recovery, so the recovery from the GELFrEE system, well, it's actually extremely high. You can think about two places where proteins might be lost. First of all, within the gel itself, and since we're applying that voltage to move proteins through the gel, it's as efficient as you can get in terms of moving them through the gel and ultimately to the end of that gel. Once they elute from the gel column or migrate from the gel column, they need to be trapped in the collection chamber, and this is what we're showing here as well. So we have a control lane, and the sample that was passed through the GELFrEE system is loaded, passed through the gel, and collected out the other end. And from 500 nanogram loadings in the GELFrEE system, we are achieving essentially quantitative recoveries when you compare these two bands. Also realizing that we're dealing with a twofold enrichment of our sample, since we loaded 200 microliters, but we're recovering the sample in 100 microliter volumes. Now that's all I'm going to show you on the single channel platform, because since then we've moved to this device, which is a multi-channel GELFrEE system. It has 8 columns, and they're using 8 independent collection chambers with each of these gel columns collected to the tube. So you can load 8 samples, either the same sample divided amongst the 8 or 8 independent samples. The operation is entirely independent, so what you load into one does not affect the separation of the other gel column. And this shows separation of 3 different proteome samples, and we can see the same type of performance across each of these gels. The reproducibility between each of these channels is best shown by putting the same sample across the 8 columns, and here I'm showing 4 of those columns. And we actually left one of the lanes empty just to illustrate that the crosstalk between channels is extremely low. You wouldn't expect to see any sample leaking between one chamber to the next. And you can see here that as we collect a given fraction, so the early fractions to the later fractions, we're collecting over the same mass range. It's not perfect. I mean, you do see that there is some variation in the time here, and one can easily contribute that to the gel columns themselves. If you see a gel column that's slightly longer than the next one, then of course it would take a little bit longer for proteins to move through those gels. Now, an interesting thing that you can do with the 8-channel device, taking advantage of that high run channel-to-channel reproducibility, is you can actually improve the sample loading. You can move it to a higher loading range. Now, if you were to overload a single gel column, so this is actually showing 800 micrograms of total protein loaded in a single column of 4 millimeter ID. What we've done here is we put too much into the gel. And it's easy to illustrate that as the protein starts to elute from the gel column, it continues to do so. So it's spreading itself out over multiple fractions. And what we'd ideally want to do is trap that single protein in one or perhaps two of the fractions. In the bottom gel, if we take that same 800 micrograms and divide it amongst the 8 columns, and then collecting fractions, you simply pool all of the fractions. So, in other words, when you pull out fraction number 1 from those 8 columns, you make a single fraction out of that. Fraction number 13 later in the run, you just take a little bit from each of those and bring them into one. And what you do there is you're working in the range that you can deal with. So we're able to trap those proteins into a much smaller number of fractions and essentially improve the resolution over a larger mass range. Coupling GELFrEE to mass spectrometry, the key here to realize is that the SDS in the sample will, of course, affect mass spectrometry analysis. So this being SDS page, the samples themselves are collected in the running buffer, the tris-glycine buffer system that we use with SDS at 0.1% or higher. And of course, we can't do direct coupling to mass spectrometry because of the SDS in the sample. So you need to consider how to remove that SDS. And there's several methods available to do so. We like the chloroform methanol water precipitation protocol in that it's extremely simple, extremely rapid to do. And it achieves very high protein yield, and it effectively removes that SDS from the sample down to 1,000-fold reduction. So that little bit of SDS that's left behind will not affect your mass spec results. So the bottom-up analysis is shown here. And we're seeing several proteins identified. We see proteins across all of the fractions that we collect. And this pattern here shows that as we move to larger proteins, as one would expect, we identify proteins over a larger molecular weight range. The overlap between the proteins from successive fractions is also assessed with mass spectrometry. And using MS, we can confirm that we see 44% of the proteins confined to one fraction, and then a further 22% of them are distributed across two fractions. So, in other words, most of the proteins are seen in one or two fractions, and things drop down exponentially from there. Now, it's kind of interesting to point out that we do see proteins that are spreading amongst a large number of fractions. And to explain that, we can look at those proteins, and if we take the number of peptides as some idea of the quantitation of proteins, the abundance of proteins in a given fraction, you can see when you plot the abundant proteins, so yeast ATP identified with up to 40 peptides in a single fraction, we see it where we'd expect it. In the later fractions, as being a larger molecular weight protein, but there is some protein detected even in the small fractions, and we're not sure if we should contribute that to breakdown products, degradation product of that ATP, yeast ATP, or something else. But it does seem to confirm that even for proteins that do spread across multiple fractions, that the majority of that particular protein is found exactly where you would expect it to be. We can do MS analysis of intact proteins. It's the same concept here where samples are collected in SDS, so of course we need to remove the SDS. Again, the chloroform methanol water precipitation. And these are GELFrEE fractions of protein standard, so the earlier fractions containing smaller proteins and the later fraction containing a larger protein. And this is ESI TOF data, and we can see our deconvoluted spectra give us a very nice clean spectra. We don't see the SDS adducts, and well, we're seeing the mass of these proteins exactly as we'd expect them.